We've introduced all the important information here. We talked about phase line equilibrium points, autonomous differential equations, the linearization theorem, and now it's time for the fun stuff. So we're going to talk about squirrels, specifically pine squirrels, all right? And we're going to talk about how pine squirrel populations can be modeled. And one of the ways of doing that is the logistic model, which we've done before. Now we're going to do the modified logistic model. Logistic model, remember, is the one that had that carrying capacity. We're going to add a new thing. So similarly to the logistic model, there's going to be some sort of carrying capacity. Now, these are very territorial animals. So if there's too many of them, they're going to start dying off. Okay, so too many is going to have a negative rate of change. I don't know how to spell. And if there's too few, and this is kind of the new thing for why it's modified, right? If there's too few of a population, then they're just going to die off. There's not going to be enough like reproductive opportunity and diversity, and they're not going to be able to sustain themselves anymore. And so that will also lead to a negative rate of change. If we introduce some variables, we could say let t be the time. We could say S of t is the number of squirrels in some area. K will be some growth coefficient for how fast they grow. N, we could say, is the carrying capacity, just like we've done before. And we're going to introduce a new constant called M, not to be confused with N, which is the sparsity constant. So just like the carrying capacity talks about, how we'll grow up to it, but we can't really sustain past that. And, if we're above it, the carrying capacity, right, they're going to be a lot of infighting. It'll be like West Side Story or something, I don't know. And it'll decrease down to that carrying capacity. Well, the sparsity constant's similar, where if we're underneath some constant, there's not enough squirrels to sustain their population, and they're going to die off, unfortunately. All right. Or fortunately, if you hate squirrels. Some people hate squirrels. So, yeah. These are some variables. So we can kind of model this by making a little plot. Oh gosh, that is the worst straight line I've ever drawn. I've drawn a lot of bad straight lines. So let's graph some information. And specifically, we're going to look at the relationship between S and G of S for the differential equation ds dt equals G of S. This is going to be an autonomous situation, because it doesn't really matter what time we're looking at. It just matters of how many squirrels there are at that time. All right. Then according to this situation, right, we know something is happening at M and something is happening at N. All right. Specifically, these are going to be equilibria. All right. If we're at the carrying capacity, we're going to stay at the carrying capacity. So that derivative ds dt will be 0 there. And specifically, this M is kind of a weird situation where if we're under M, we don't have enough population to sustain, and we're going to die off. And if we're over M, well, then we're going to grow up to N. But if we're M exactly, we're neither growing nor decaying. We're at this weird sparse, like very, very, we'll talk about this later, I think, when we talk about bifurcations, but we're at like a very precipitous point, all right, where it could go either way. And we know what this graph is roughly going to look like, right? G is the derivative of S. So G will be negative if we're under that sparsity thing. It'll be positive if we're between here, and G will be negative again if we're over the carrying capacity. When is the rate of change negative? When there's too many squirrels and too few squirrels. Otherwise, the squirrels are going to be growing. Negative rate of change, G, is the rate of change of S. So G will be negative when there's too few or too many. Otherwise, it'll be positive. We could have some kind of, shape, right? We know the shape of G should look something like this. And we know what parabolas look like. We can plot a parabola that looks like this. We can use this information to say, okay, there's going to be some vertical scaling constant. That's the K that we used before. And, also, We also know there's an equilibrium point at 0, right? If there are no squirrels, there will never be squirrels. So maybe we adjust this a little bit because this is continuous. So there's a 0 here. Now we need a 0 for the n. That'll be just like the logistic model. Remember, if we have something like this, then if s is equal to n, this term is 0. And we can do something very similar with the m term, but flip the order so that we have negatives in the right place and positives in the right place. You don't have to be able to come up with this on your own, okay? But you should see where it comes from. This is ensuring that everything is the right zeros, and then the order of the terms within each term, make sure that we're positive and negative in the right spot. And so this is what's known as the modified logistic model. And again, we could solve this differential equation. You could solve it yourself. This is autonomous. All you have to do to solve this differential equation is integrate 1 over ks, 1 minus s over n minus 1. And you all could do something like this in Calc 2. What is this? This is partial fractions, everyone's favorite integration method. We're not going to do that right now. Okay. What we are going to do is look at the phase line and look at the slope field. So we know the phase line here. We're going to plot the equilibria, right? We don't have y, we have s. We have s equals 0. We have that small thing for that sparsity constant m. And then we have the carrying capacity n. Right? We know the derivative is positive here, negative here. All right, positive here. All right. What if s is negative? If s is negative, we're not dealing with negative squirrels here. But if we wanted to, we could continue it. If we wanted to talk about negative squirrels and what that meant, we could. I'm not going to talk about negative squirrels today. All right. And then we could use this to plot some solutions. Right? A sketch of solutions. We're going to be good mathematicians and label our axes. This is time. This is the number of squirrels. We have our equilibrium solutions at the carrying capacity, at the sparsity constant, and at 0. And we know that solutions are going to be looking like little logistic curves themselves. Remember, because we have the required components, this will be shooting off to positive infinity if you go to negative time. And something interesting would be happening if we talked about negative squirrels as well. But yeah, depending on what your initial condition for the number of squirrels is, this is how it would change. Right? If we were above the sparsity constant, if we had enough squirrels that if we had enough squirrels to reproduce, then they're going to grow up to that carrying capacity. If we had too many, they decay to that carrying capacity. If we didn't have enough to reproduce, they're going to die off. And of course, if we're at one of these blue values, it's just going to maintain and the population will be constant. All right. That's pretty much it. That's the modified logistic model. We get to use some of this stuff. We didn't really use the linearization theorem, but we could. Linearization theorem would have us look at the derivative of the right-hand side. We'd have to FOIL all this out to really make good use of it. And then we could use the linearization theorem. So, well, you can use that on your own. Use it in the homework, on the quiz. All right. That's pretty much it. Let me know if you have any questions, and I hope you enjoyed this section on phase lines and equilibria. We talked about classifying equilibria. We talked about creating phase lines. How can you use those phase lines to work with autonomous differential equations and sketch some solutions from phase lines. We had a lot of these cool graphs where we talked about the relationship of the function value with its rate of change, just like we did a lot in calculus. You probably hated it in calculus, but hopefully you love it now because you see why we use it. And yeah, should be good to go. Enjoy.